Okay, so now we're going to move it on a little bit, looking further at some space requirement issues. The thing we're going to look at mostly next is line balancing, but before we do that, I just wanted to talk a little bit about visual management because it is sort of part of space management. I don't even know if it really goes here. It kind of is about lean manufacturing concepts. But one of the things is that you have posted performance indicators throughout the facility. You also have signs that show where things are and like what departments are where. You have 5S things like a place for everything and everything in its place. And these are just good visual management techniques, mostly associated with lean manufacturing, but they are part of your space and they should be planned into that. Whenever you do a facilities design, you should include taping off of areas and identifying aisles and things like that. So now we're going to move on to line balancing. And the reason it's here is because if you have a production line as opposed to a product, and if you have a production line instead of a process department, you'll be using line balancing techniques to figure out how exactly to balance that. It also is related to the number of machines in a situation. So the goal of line balancing is that you have smooth production that's going to meet demand. And one of the sort of cornerstones of this is that you try to meet your demand. The line is balanced depending on what the customer is demanding. And this helps you to determine the appropriate tasks for each workstation. So there might be multiple tasks done in one workstation, or determine the appropriate number of workstations if there's multiple workstations. And this starts with a concept that's called takt time. You might have heard of this before, but it's the number of the time that a component spends at each workstation. And this is dictated by demand. So takt time is the minutes available per year divided by the demand per year. And that's how we get that number. We just say, okay, how much time do we have? And how many items do we need? And so what does that mean about every time, how much time an item has to stay in the workstation? That's also equal to how often a finished component comes off of the line. So if you think about takt time, it's kind of like a beating of a drum. That's the word takt. And it indicates sort of a beating that's associated with production. This is the operations process chart for the case study that we talked about in a couple videos ago. And what I'd like you to do is to determine if a table manufacturing is set up in line to produce tables, calculate the takt time of the demand if it's 23,000 units per year and the company works one shift a year. So you have both of those things that you're needing. You have the units and you have the time required. This is actually the thing, so that's what the requirement. So go ahead and try to do that in a minute. Maybe stop the video or just try to do that calculation. So I'm probably impatient here and I want to give you the answer. So the answer is the total production is 23 units. The total minutes available in an 8-hour day, 5 days a week, 50 weeks a year is 120,000. So that means that you take the 120,000 minutes over demand. So the units have to be a time per unit. So it's a little bit less than a minute per unit that you need to be doing the takt time. So every minute a finished table has to come off the line. We're going to use this in class when we look a little bit more at some takt time about line balancing in that particular case study. But I'm going to go through a couple examples here because it's a little bit different depending on whether the task time is less than the takt time or greater than the takt time. So if the task time, the little bit of time that you need in order to make a part, if you've broken it down like the things that you've time studied, those elements, if those are greater than the takt time, then what you end up doing is actually doing a calculation on the number of machines required to do the particular tasks. So in this case, this example is the demand is 320 units in an 8-hour workday, and so we have to calculate the required takt time for that. And then sorry about that. And then we also are going to calculate how many people should perform each of the tasks in order to produce the required in the amount of time. And that's a list of workstations. So whenever we put together a line balancing, the judge that we use is efficiency. And that means that we want to minimize the amount of time that's idle for any worker, and we want to maximize the amount of work time. So the way we do this calculation is it's expressed as a percentage, and anything over 80% is a pretty good number. And what we're doing here is we're doing the sum of all tasks, which is the work time, all the work time required, divided by the number of the work available. So this is the work required, and the work available is the number of workstations times the task time. Because if we have 5 workers and they're working all the time, then that's what will be the required amount. So let's look at this example. The takt time is 1.41 minutes per unit. So that means that if the task takes less than 1.41 minutes, you just have one person working on the task. If it takes more, then you might have to have multiple people working on the task. So in this case, I've filled it in there that for the first one, it's that 1.25 is less than, this 1.25 here is less than the 1.41, so I can just have one worker doing that. In this case, 2.38, it's actually less than the 2.82, which is the fully involved 2 workers, so we can have 2 workers doing that. And we just go down here and assign. You can see the 3.84, we actually need to go up to 3 workers. And all of these task times that are required to make this part, and we sum up all the workstations. So there's going to be 13 workstations working, and there's going to be 3 of them on this task, 2 on this task, etc. And then when we do a calculation of that, I'm summing all of the task times, which are these along here, all of those added up to 1637, and then I divide that by 13 workstations times the task time, which is 1.41, and I express it in 100. So that's an 89.3%. Efficiency for this particular line. That's actually a pretty good efficient line. That only about 10% of the time are the workers not working. Now we're going to look at the next case where the task times are less than the takt time, and this requires some sort of line balancing. And when you're doing this, you really do need to know not only the tasks, but you also need to know the precedence. And what you end up doing is grouping tasks into workstations. Like, okay, workstation 1 is going to do task A, B, and C. Workstation 2 is going to do C, D, and F. Things like that. And then you calculate the efficiency. So again, it's still the same equation where we have the sum of the tasks divided by the takt time times the number of workstations to get to that efficiency value. When we look at an example, so the goal here is to group all of these tasks, A through K, into workstations. They each have this amount of time that's required to do, and then there's a precedence. Like task C, it can't be done until A and B are finished. Task D can't be done until C is finished. So, and in this case, we want to produce 300 units in 450 minutes. So we go ahead and calculate the takt time. Oh, I shouldn't have done that. Takt time is 1.5 minutes per part, so because that's the 450 divided by 300. And then we need to create a precedence diagram, which is what I did here. So you can see, remember I said A and B have to be done before C. I did that. I lined those all up. And so this tells me that I can't really group something together. If I want A and B together, I can't also group I, because C and D need to be done before I. I can group all of these together because there's no precedence that's violated. But that gives us an idea of how we're going to group it together. So we group tasks together so that there's less than 1.5 minutes. So in this case, if I group, and this is just trial and error, if I group A, B, C, and E together, then that sum of that is less than 1.5. And I can group F and G, group D all by itself because I can't put it with H, that's over the 1.5, and I can't put it with I, that's also over the 1.5. So these also have to be done separately and those together. So what happens now is I have 6 workstations, and that means that if I calculate my efficiency, I'm calculating the total time, which is the sum of all of these little tasks times, divided by 6 times the takt time, and that's a 73.4% efficiency. And we can try different arrangements to see if we can get it to a lower number of workstations. It's totally possible to do that, but that is the process associated with this. Now what we're going to do, I'm going to give you a simple number of machines problem. No, not, I'm going to give you a simple line balancing problem, and then we'll work on one in class also.